All right, so as, I'm sorry I don't know your name, but Mark just indicated I'm going to be talking about scalability. In particular, I'm going to be talking about superscaling, which probably a lot of you haven't heard of before, so I hadn't either before 2010. And so this is what I'm going to explain to you ultimately, but to get there, I have to be able to tell you something about how I analyze scaling. So that's what I'm going to start off with. However, before I get going, I just want to acknowledge some people from LISA, because this is actually the first time I've been to LISA, and I must say I'm very impressed. So I want to thank Pat Cable for inviting me, and Hilary Hartman for looking after me as a LISA newbie, and Rick Farrow, who's censored my slides for the Sunday tutorial. And all of the conference organisers have had a great time, actually, so something new for me. And of course, all the interesting people I've met here at the conference. So what is this talk about? Well, it's not actually about that. It's about this. So you're going to see a lot of plots or graphs that look like this with speed up, which I'll define in a minute, on the y-axis, and typically processes or cluster nodes on the x-axis, but it could also be load generators or whatever. The whole thing's quite universal, as I'll explain in a minute. That's why I call it the Universal Scalability Law. So I come at this from a rather different approach from most people. For me, people discuss scalability, but they generally discuss it in qualitative terms. I think the main reason for that is they don't know how to discuss it in quantitative terms, so that's what I'm going to try and show you. And they're looking at it from an operational point of view, which is perfectly fine, or from configuration recipes, and which kinds of applications and accelerators and so forth to use, all of which is interesting, but it's not really scalability. And the rest of it is just lots of words, usually on blogs, and rarely are there any numbers associated with it. So what I'm going to show you is that the numbers are critical, and you have to understand how these numbers come into play in order to even talk about scalability in a coherent way. Because otherwise you can't do any kind of cost-benefit analysis without the numbers. And why should I believe somebody's configuration over somebody else's configuration unless I can actually have some kind of sense about cost-benefit? Should I really migrate to that thing or not? So we need to measure scalability in an appropriate way in order to quantify it. The question is, what is the right way to do that? So one of the important messages is that you can't do it by looking at monitoring data from prod systems, which of course you've been looking at endlessly in this conference and most other conferences for that matter. The human brain's not built to comprehend that kind of data. So you need to transform these typical time series that you see in these ad nauseum strip charts and whatever fancy GUIs are available today from data into informational metrics. So that's largely what I'm going to show you, but I'm going to show you what I think are some very interesting examples of that. So I hope you'll find that interesting too. So in order to quantify things, we need numbers, but we need numbers in a rather special way. And I've just lifted this thing from Google back in 2005. They were talking about the scalability of MapReduce and so forth, and this is just something I picked out of one of the papers. It says basically in our test it was 0.98 of all of the machines was scalable in some sense. Now if you translate that, that to me says that MapReduce is scalable in the sense of being about 98% of linear. So what they mean is if you look at the little graph there, this one over here, it's more or less a straight line. So the idea is it's a straight line, but it's not quite 1-to-1 ratio. It's just a little bit under, but it's 98% there. But even that's not good enough. Certainly it's a number. It's not just a qualitative statement. So it's an improvement, but it's still not good enough because the fact of the matter is the scalability is a function, not a single number. And the reason for that is because I'm sure you're all aware that as you scale the systems up, typically they show some kind of diminishing return characteristic. And it's actually that characteristic that I want to quantify. So we want to be able to express these overhead and losses in a quantitative fashion. And for that, we need a function. The function, by this I don't mean Java function, I mean mathematical function. And the question then becomes, okay, this is what I need to quantify it, what is that function? And that's the next section. So rather than go through all of the mathematical proof of all this stuff, I'm just going to show it to you diagrammatically. So this is ideal linear scalability. This is what people notionally have about building large systems. If you didn't, you would probably quit doing it because it would be too devastating. So this is the goal. Everybody's optimistic that they can get there. This is the kind of thing they have in mind. And you may miss it a little bit, but this is what you're shooting for. So once again, this is speed up on the y-axis, which I'll explain shortly, and the number of processors typically on the x-axis in terms of scaling up something like a cluster. And we're going to be talking about Hadoop, so I'm talking about clusters today, actually. So think of the straight line as being equal bang for your buck. You buy more capacity, you spend the money on more capacity, you get the associated performance and scalability as a consequence. That's the assumption. But of course, in reality, as we saw somewhat with the Google statement, there are diminishing returns. That means that there is every opportunity now not to meet the linear scaling and to in fact curve away from it, fall short in some sense because of these overheads. And this in fact has to do with contention within the system. By contention I mean contending for shared resources. Think queuing if you wish. I don't have time today to explain all this in great detail, but I hope you get the sense of it. So when you see the thing falling away from linear, in general this has to do with a contention cost of some kind. That's an important word that I'll come back to later. And of course the contention can go on growing as you try to scale the system up. If there's contention for relatively few resources from time to time, then on average the thing is going to fall away from linear in a severe way, in such a way that ultimately it will reach a ceiling. There's going to be a horizontal limit to how much you can scale up. It's a horizontal asymptote, and we can even figure these things out, although I won't be actually showing you that today. And you can see that the diminishing returns are represented by the triangles. These two blue triangles have the same base width, but obviously their height is different. Down near the origin, it's pretty close to 1-to-1, which is how you think you would like to keep going. Every time you add more capacity in another triangle, you'd like to increase by a 1-to-1 ratio. But in fact, when we're over here, you see that the vertical rise on the triangles substantially less than that. But it can be even worse than that. You can have negative returns. And this has to do with what I call coherency factors, and that means the time or the penalty taken to make non-local data consistent across all of the resources where it's residing. So these are some of the factors in scalability. So basically linearizing, falling away from contention, getting worse and heading for a saturation limit, and then possibly even taking a nosedive due to coherency effects. This is a sort of classic scalability characteristic, and I can now show you that I can classify all of those bits and pieces or components of scalability into a single, relatively simple equation. So I want to be able to express the x-axis, which is the number of processes or the number of processors. Today, mostly I'm going to be talking about processors. And that represents the scale-up of the system load. So more processors doing more work means more load in the system. The question then is, how does the system respond to that? Is it equal bang for the buck or something less? So I'm going to call that the speed up. And you've seen that already as a label on the y-axis in the graph so far. But think of it just as a throughput, because any function that's concave like that does represent a throughput. It's not response time. And it's a normalized throughput, so slight technicality. That's just to get all the numbers to work out consistently. But just think of it as speed up as a kind of a throughput. So now, new question. What does this speed-up function look like? Well, it turns out it's what's called a rational function, something that I devised in 1993, so I've been banging on this for quite a few years. And here's what it looks like. So the thing on the left-hand side is the speed-up function, the response of the system to the load that's applied, normalized throughput for us today in this conversation. And it's a ratio where the top of the fraction is represented by simply the number of processors or nodes or in the cluster. And the interesting stuff goes on in the denominator. There are three terms you see here. And what do they represent? Well, think of the plots that I just showed you. The first one of these three C's is the concurrency. That means if the term here in the pink oval and the green box, if they were both zeroed, and that is to say didn't apply, then this would just be P over 1. That just means it would be linearizing. That's equal bang for the buck. So that's apparently captured. The next C is contention. I just mentioned that a minute ago. That's why it falls away from linear. And the rate at which it falls away from linear is controlled by this little coefficient out here, which I'm calling sigma, which has a value between 0 and 1, or if you prefer, between 0 and 100%. So that gives it the magnitude of the contention in the system. And then finally, the third C is the coherency term I alluded to a minute ago. That's the thing that causes it to roll over. And you can see that it's got its own separate coefficient, which I'm calling kappa here. And similarly, it's a number between 1 and 100%, representing the degree of coherency penalty in the system. So that's it. This is the model. And what's interesting about this now is that, and most people don't get this, the idea is I'm not going to validate the model. I already know the model's valid since 1993. What we're going to do is validate the data. The reason is that data comes from the devil. Only models come from God. So it's always a question of, is the data conforming correctly or not? If it's not, then something's wrong with the measurement process, because I will fight to the death over the model because I've made it so simple that in principle it really can't be wrong. And what's new for me is that it even handles superlinearity, which I haven't shown you yet, but that was actually a shock to me. Nobody was more shocked in this world about superlinearity than me. I want to take the data. So the data here is going to be represented by throughput. My notation for throughput typically in my books and so forth is just capital X. So that's a throughput. Throughput is a rate, number of connections per second, kilobytes per second, whatever it is. And the normalization part just means I'm going to normalize it to the throughput for one of whatever the entities are, one node in a cluster, one core in a CPU module or whatever. So that's the data. So now this is just coming from measurements. That's this part of it. And I'm going to define that to be the speed up. So that's what I said it was before. It's the normalized throughput. So there's the symbolic representation of that. The thing on the left, on the far left, is the normalized throughput ratio. And that does represent the speed up as measured. But we're now going to make the measurements meet the model. So here's the model. This is the equation I showed you on the previous slide. And these two things have to jive. That's the point. Now you could ask, well, I've got some data. I do this little bit of magic with the normalization. That defines the speed up. That's all okay. That's just arithmetic. I can do that easy. And the point is the model, that has a certain form. So how does the model adjust to try and express what's going on in the data? Well, that comes from these two little coefficients. That's the contention factor, the sigma coefficient, and the coherency factor. The only thing that can change, once I have a certain configuration, the P is fixed. So let's say I had 100 nodes, P would be 100. So everywhere you see a P in that equation, it's 100. That's fixed. The only thing that can possibly change is the coefficients in the equation, the sigma and the kappa values. And it will adjust to try and fit the data. I'll show you how this goes in a second. Now, what's interesting is not the equation so much, but to actually plot it out, at least in a theoretical sense, and that's what I'm showing here. So there, the red dashed line you see here is linearizing. That's equal bang for the buck. And then it falls away, as I showed you in the previous slides. So the dark blue curve here represents the case where it's just falling away and, in fact, rising up to that asymptotic ceiling that I mentioned before. And that would be the case if the kappa value, that's to say this term, was 0, because there's no coherency penalty, let's say, in the particular system. Then only the first two terms would be active, and that would give you the dark blue curve. As kappa, the kappa coefficient, gets bigger than 0, what happens now is something dramatic, and that is that the curve moves down this way. And what I've indicated by these little red triangles is the peak or the maximum in the curve. And you can see that as I increase the kappa value, the curve not only develops a peak, that peak starts to move back towards the origin. This is disastrous. So the point being, I'm not interested in fitting something that's a disaster. I would like to know what might be contributing to that disaster so that I can actually remove it. And if I know the value of kappa, that's to say the coherency coefficient, then that gives me some idea of how much work I'm going to have to do to get rid of it. The purpose is to get rid of it, not to model it, to get rid of it. All right, so there's the equation. That's the thing I call the Universal Scalability Law, which I just mentioned back here. There's the title. So I call this the Universal Scalability Law. The reason I call it universal is because it basically fits everything that you would particularly, especially have in a system, but in particular the things you don't want to have, such as the coherency penalty. So now the question is, how do we determine this sigma and kappa? We've got our model, we've got our equation, we can put numbers in, so we're well on our way to doing quantification. And I've shown you what it looks like theoretically. Now I'd like to try and apply it to some data. Where is that data going to come from? Well, you could try to do this stuff by brute force. And in fact, people have tried to do that. Well, good luck with that. That's the hard way to go about it. The other point is, as I mentioned earlier, you have to have controlled measurements, not monitored data. That won't work. So I have in mind something like J-meter. So even if you're in ops and you're not measuring this kind of stuff, you may in your organization have people who call themselves performance engineers or QA people who may have this kind of data. So you may already have it lying around, you just have to go and get it if you want to do this kind of analysis. And that's commonly the case, by the way. So rather than brute force, the clever way is to use statistical regression. And there's been a few talks about that here and some Sunday tutorials on those subjects. So that's pretty nice. So some of you already have a background in that. I'm not going to get into that in great detail today. I'll just show you how I use it. So I'm going to use R. This is the open source package that's been developed, depending on how far back you want to go, for the last 40 years since it started life as S at Bell Labs. So it's really been shaken down. It's, I mean, it's not exactly bug-free, but it's asymptotically bug-free, let's say. And on Sunday, there was a tutorial for sysadmins about how to use R. I think it was going on at the same time my tutorial, so I didn't actually go to that one. And the functions that I'm going to use in our NLS, which does not only regression, but nonlinear regression for me, and that's the magic because it will actually calculate for me sigma and kappa, that's to say the contention coefficient and the coherency coefficient in one swell FOOP. And then there are other functions like optimize. I can even calculate these things when I don't have the single node throughput value to do the normalization. I don't even have to have that particularly. It's nice, but if I don't have that, I can interpolate what that should be using functions like optimize. And then I can predict and interpolate and extrapolate from the data. And of course, I can plot this stuff out. And the plots I'll show you today are in fact plots from R with its various bells and whistles. Most of the bells and whistles I don't even use because I'm not interested in some fancy graph. I'm interested in what is the graph trying to tell me about the data. So let me now show you some examples. So how many people here use Varnish, just out of curiosity? Okay, you're familiar with this. You can tell me more about it afterwards, perhaps. So for those who don't know, it's basically an HTTP accelerator, essentially a caching engine. And the most important point for this discussion is that the general claim, in particular by the guy who did most of the development, who's, I think, somebody from Denmark, if I remember correctly, the claim is that it's highly scalable with the implicit idea that, you know, it's really pretty linear. And I've seen any one of a number of these claims written as words, but I've never actually seen the numbers. Has anybody actually seen numbers that support the idea that Varnish is linear or near linear? So the question is it? And how the hell am I going to tell? So my colleagues that I just mentioned in the previous slide from Finland had done such measurements using J-meter, I believe. And so I took their data, read it into R, create a data frame, and create the plots, and here you see the table. So what we're looking at here happens to be the number of load generators. There's not processors in this particular case, so it's a fixed number of CPUs, let's say, in a monolithic box. But the x-axis is representing the load, and the load in this case is the number of generators that are being fired up by J-meter at each load point. And the dots that you see here are the measurement values of the throughput at that particular load point. So read off the x-axis, that's the independent variable, go up to the y-axis and read across what is the speed-up value or the normalized throughput. That's how it works. What do you think? Looks pretty linear? Not quite good enough, because let's put in the equal bang for the buck line. That's the red dashed line. I'm going to put that in. I think every plot I have has this today. And you can see, looking at data like this with any kind of reference frame is not cool, because you're going to get yourself bamboozled into thinking that it's linear, when in fact, it's not exactly linear. It's a little bit more like that Google statement. It's kind of like 98% or 95% of linear, which is still damn good, by the way. So I'm not casting no dispersions on this particular set of data, but now I've got a reference against the equal bang for the buck line, the theoretical linear bound, I'm going to call that. And you can see that it does slightly fall short, and the fall away does grow bigger, but it looks pretty constant other than that. Now, here, by contrast, is the curve generated by the USL. That's the blue line. That's the USL as the Universal Scalability Law, the equation I just mentioned a minute ago. So now I fit that data to the USL equation, and it generates the blue curve that you see here. And you can see, naturally, the curve doesn't go through every data point, and nor should it, because this is a statistical analysis. We're not doing spline fitting, we're not doing computer graphics, we're doing statistical analysis. So it shouldn't go through every data point, and in fact it doesn't. But you see the difference between the actual data and the USL curve is not bad. And notice down here in the little legend that the sigma value is 2 by 10 to the minus 4. That's extremely small, which it has to be because if it was bigger, it would fall away faster. So I'm expecting sigma to be small. It in fact is, and the kappa term, that's the coherency part, is 0. This, in fact, fits with the notional claims that I've seen describing Varnish. But now I have it in, quantitatively, and I can quantify its scalability in terms of sigma and kappa. A small number and a 0 number. That kind of jives. I can go even further. This is the interesting part about doing the scalability modeling. This is now projecting the USL model fitted to these data, and you see that data range goes up to about 400 generators on the x-axis. But there's nothing to stop me from now projecting that value out to 4,000 or 5,000 generators. There's no data out there, but the data is down here towards the origin now, and you can see, in fact, it does fall away from linear, but it's another order of magnitude, so it's still doing extremely well. And you can see that it's gradually heading up for this asymptotic ceiling, but it's nowhere near it yet. So probably do another order of magnitude before even that became effective. And then ultimately, one day, I'd like to see somebody who could actually do measurements in this region. It may or may not happen. And that will either confirm or adjust the USL model accordingly. So this is how the game works. So it's not just a matter of fitting the data, it's also a matter of committing to the results of that fit and then projecting those data in terms of a scalability curve. And this is what it looks like for Varnish. So not casting aspersions on Varnish at all. In fact, it looks pretty good. But now I know I have a better sense of what it looks like quantitatively than just this notional terms of it's near linear or 98% of linear. Second example, Memcached. How many people here use Memcached? Cool, okay. So this is taken from a presentation we gave at Velocity back in 2010, just to show you. So this is all about scale out versus scale up. You're familiar with all that. The idea of Memcached is that it provides a distributed cache for key value pairs. You preload the data out of the DBMS so that you don't have to keep going and fetching through the database management system. And the other idea is that you deploy this on cheap servers, possibly servers that were the previous generation before you did the latest roll of the hardware up to more recent technology. So let's say, for example, that you deploy it onto tiers of cheap older CPUs, but at that point, let's say they're not multi-cores. And back in 2010, that was kind of the roll point for a lot of people. So if Memcached was single-threaded, it wouldn't be too much of a problem because it would be fine for single processors, if you imagine a single processor on a blade, for example. But in the next roll, say in another 2 years, then the current generation, let's say that's multi-core. Now the question is, how well does Memcached play on multi-core now? So if it's single-threaded, that would be a problem. So it turns out not to be single-threaded, but it's not terribly threaded. And what do I mean by that? Here's the data, measured by some colleagues of mine at Sun Microsystems before they morphed into some other company whose name I forget right now. And you can see, in fact, this is sort of linear for some time, but then it rolls away from the linear bound, reaches a maximum, a peak, and then rolls over. And the peak is at around about 6 threads. So let's say it would be okay on a 6-way multi-core, but beyond that, it wouldn't scale very well. So I analyze this in R using the USL. Here's the USL equation represented in R, just so you can see what it looks like. And then it calculates for me the sigma and the kappa values directly as outputs, so that's where I get the numbers from. And now I plot the USL curve corresponding to those data, and that's the blue curve you see there. And the sigma values are calculated here, and I put those in the legend. So you can see now the sigma value is not 2 by 10 to the minus 4, it's something more substantial. It's about, 2.5%, something of that nature. And the kappa value is also on the order of 2%. So that's why it's rolling off fairly quickly. So the idea now is there's no point projecting that because it's already in a nosedive configuration. So there's not much point in projecting it. What was more useful to do is to see, can we move that maximum out? And in fact, Sun did a significant amount of work and introduced a patch which as far as I know is only specific to Spark, the Spark processor, because they had quite a large number of cores even in 2010. I think it was maybe a 32-way or something, or maybe even higher, maybe 64-way, I'm not sure. And so they introduced a patch into the Apache Memcached project, and this just to give you an idea. So there's the lower curve. This is we were looking at this region just in the previous slide, less than 10 threads, and they were able to, through a sequence of steps, able to rescale this thing out to something like, let's say, 40 or 50 threads. So there's another application of the USL. And you can see that the curves look different, but in fact it's all the same equation, just the only variation is in the sigma and kappa coefficients in the USL equation itself. I had to throw this one, I threw this one in this morning. As you've noticed, there's free copies of Login from last month out on the table there in the lobby somewhere. If you go to page 23 and look at figure 4, you will see these data. So this is Sirius, which is this is Comcast's version of Zookeeper, if you're aware of that. So this is a distributed coordination system which uses a voting scheme, and this is rather fascinating to me. So what I've done here is I've applied the USL to these data, and of course the data actually starts here. This is a dummy value that I'm using to normalize to the single node, but in fact in the Sirius system or in Zookeeper, single node doesn't work. You've got to have at least 3 nodes in order to get a majority vote. So the default baseline system is 3 nodes, not 1. So this is just for the purpose of the USL, so that's why the dashed line is there. And then you can see the scalability starts on the downhill slope of the peak. What's interesting about this is how it has to be. It looks awful just generically because you've got negative scalability. On the other hand, there's no way out. This is how it has to be. So the only question remaining is how efficient is that negative scalability? How fast does it head towards the x-axis? And if it's fast, can we do something about that? And I haven't had time to analyze Sirius versus Zookeeper, so I don't know what the answer is right now. But you can see once again the sigma and the kappa value, and these are the data. This is identically taken from the figure in the Login, if you're interested in that. So this is yet another capability of the USL. I've never seen data like this before, and yet it works. And it has meaning, even though it looks weird when you first look at it. All right, so let's get to the main topic, which is supersizing, superlinear sizing. And this is work which I've been doing with a couple of colleagues of mine and will appear in ACMQ, so keep your eyes open for that. So I don't have time to go into all the details, so I'm just going to give you the quick tour of how this goes. So remember this? This is the qualitative plot that I put up earlier. So we've discussed linearizing, that's equal bang for the buck, that's the dashed line. We've discussed now sublinear, maximum, negative scalability. You've seen a few examples of that now. That's how things normally go. What we're now talking about is a curve like the blue one that goes in completely the opposite direction. That's called superlinear. So anything above the linear bound is superlinear, in other words, above linear, and anything below is sublinear. Sublinear is the norm. Superlinear is very strange because it represents something that's more than 100% efficient. How do you get that? Well, lots of people claim to have seen it and have discussed it. Here are some references that I've uncovered. So, and I will say this, if you do the measurements in the right way, there's every possibility that you can see it on certain systems. So I'm not claiming that the measurements are wrong. That's not the point at all. There's nothing wrong with the measurements, and if you and I went and repeated them, we would get the same results as these folks who discuss this stuff. So the issue lies actually somewhere else. Just to give you an idea, this is Hadoop exhibiting superlinear behavior because it's on the upper side of the linear bound. These are data points. These are our measurements actually, and you can see without doing anything more, it's superlinear. It's fast. It's scaling faster than linear. And by the way, if you have an application that works like that, I suggest you ship it. But I don't make products, so I'd like to know exactly where that's coming from. This reminds me of perpetual motion. Perpetual motion is something that's been going on for thousands of years. However, more recently, in the last couple of centuries, we have something called the conservation of energy law, which most of us believe in, and I certainly do. And so every perpetual motion contraption, no matter what it looks like or what the claim is about what it's doing, must violate the conservation of energy law. So if you have that in mind and keep that firmly in mind, then there must be something wrong with the contraption, because super efficiency means that it's producing more than 100% output. It's producing more out than you put in, and that violates the conservation of energy law. Now, even if you understand all that and you did some undergraduate physics and you believe what I'm saying, and you believe the whole thing is wrong, that the contraption can't work that way, proving it is the hard part, because this is basically a debugging problem which can be very tortuous. So superlinear scalability, I claim, is in the same boat. It's exhibiting measured speed-up performance that exceeds 100% of the available capacity. Nice if you can get it, but not likely, because it violates the universal scalability law. And again, proving it is the hard part, not guessing that it's probably not right. But once again, it takes serious debugging effort. I'm not talking here about program debugging, I'm talking about system-level debugging. So let me give you the background to how we actually generate that data that I just showed you. That was real data. So we have to have a controlled environment. There's a similar idea to JMeter, but we used TeraSort, which is a well-known workload that has been used to benchmark Hadoop MapReduce performance. So the idea is basically to sort 1 terabyte of data. We didn't need to do that. We weren't doing benchmarking, and we actually only needed to use 100 gigabyte of data for the input to exhibit the effect. And the other thing that we did is we simulated the whole thing on EC2, Amazon EC2 in the cloud, because it's more flexible, it's cheaper, we could scale up rather than trying to reconfigure a physical cluster. And it enabled us to do many runs, and some of them we were able to do in parallel. So the table at the bottom just shows you 2 of the main configurations that we used. I call it Big Mem and Big Disk, just to distinguish them. Amazon has a much more funky way of categorizing them, but it's too mysterious. So I'm just going to call it Big Mem and Big Disk. The main difference is that Big Mem has a single disk instance storage, and Big Disk has 4 disks. And then the other variations are in the number of CPUs and the amount of memory and the network performance. But turns out that's not going to play a big role as far as we can tell anyway. MapReduce, there was a previous talk about MapReduce, so you probably already got the background on that. But basically the idea is that you partition the 1 gigabyte of data, or in our case just 100 gigs of data, across the number of nodes that you have configured for the cluster, from 1 to 200 in our case. And you split it up, and then the idea is to sort it, and so you chop it up into basically equal pieces. The mapping function then takes that input, manipulates the key value pairs, does a sort operation on them, and partitions that out as output, and then after the mapping phase is complete, that data is then exchanged between the mappers and the reducers. And that's actually the shuffle part that I heard mentioned in a previous talk today. So this is the shuffle exchange that goes on between the mappers and the reducers. Actually, it's the reducers who make a request for the data from the mappers. And then they do the merge and the final reduction. And at the end of it, you should be able to concatenate all those files and get a completely sorted file in order. In our case, we had some interesting numbers here, just factoids. 840 mappers total, and 3 reducers per node. And on a single node, the runtime, even for 100 gigabytes, is about 5 hours, just to give you an idea. And then we use Cloudera distribution, Apache were, and some of the performance statistics were just coming from Linux performance tools. So here's the data. So this is a set of data that goes up to 50 nodes on the x-axis. So these are now EC2 nodes. This is Big Mem. Speed up on the y-axis again. And the data is the black dots, and the blue curve is the USL fit to those data using nonlinear regression. And you can see there's a peak there just below. The peak is actually at 47 nodes, according to the USL. So the USL, the important about this particular graph is that the USL is predicting that even though these data are superlinear, the performance, the speed up, will cross back over the linear bound, which is not obvious at all. Now it turns out that when we take data from a larger scale set of clusters, up to 150 nodes, for example, these are the 2 new data points, roughly at 100 and 150, And in fact, you see they do cross back over the linear bound. What's happened, of course, is there's more information now because we've got new data, so the USL adjusts itself accordingly. So the sigma and kappa values have changed. The main point here is that even if you're superlinear, at some point you're going to cross back over that linear bound. I'll come back to that in a second. So what happens, if you notice the value of the sigma coefficient in the graph there and the previous one there, you'll see they actually have negative value. So that's very strange, and this is the thing that got my attention back in 2010. So if you have a negative value for sigma from doing the nonlinear regression of such superlinear data, that's the proof that superlinearity really is there. So we have these negative values, so what does this sign mean? So we can think of the positive value, which we normally have, as being responsible for falling away from linear due to various kinds of overhead in the system. So positive means overhead or a loss. Negative, therefore, by flipping the logic, must mean that there's some kind of credit that's allowing me to run at more than 100% efficiency. And the question then is, what is this credit? So it turns out, without going into the details, it's tied up with the number of, one way of looking at this is that it's tied up with the number of actual spindles that are attached to each node, either 1 or 4 in our case. 1 is a big mem configuration, big disk is 4 spindles. And I'll just show you this graphically because there's no time to go into the details of it. So this is an example of superlinear data on Hadoop, on EC2, up through 10 nodes. But that's on a single disk because that's a big mem node. Now I'm going to change to a big disk node. That's to say 4 spindles per node. Watch what happens to the data. You see that? Animation. So even at 10 nodes, what happens is if I add more disks to the node, the superlinear effect goes away because now those data points are either linear or sublinear, not superlinear anymore. And that's the part of the explanation that comes out of debugging exactly what all this means, and that's quite complicated. So just very briefly, the apparent capacity credit is really somehow related to this I/O bottleneck on a single node where you have a single disk, the big mem configuration. The credit comes from the gradual reduction in the I/O constraint as you add more nodes, but it's very slow. So it sort of relaxes the latent I/O bandwidth constraint that you started out with on the single node as you increase the number of nodes up through, in our case here, 10. And the I/O bottleneck further induces random retries in the reducer process. I don't have any time to explain that today, but it causes a kind of a stretching in the amount of time it takes to actually do the workload, and that actually has a significant impact on the normalization where you divide the throughput by the one node throughput. That's the speed up value. So the details of this will appear in the ACMQ article. Just one other thing I thought of as I was putting these slides together this afternoon. If there's any Hadoop experts in the audience, please tweet me up because we have some questions and you might be able to help us out. And of course, we'll have to give you credit in the upcoming ACM article. So in summary, USL requires 2 coefficients, sigma and kappa, that's to contention and coherency. As a general matter, both of those are positive and should be positive to give you a speed-up function which is concave, that's to say going like that. If you have convex efficiencies, which is what you need to get this superlinear effect in order for it to be more than 100%, although they do appear to exist, and it's true that if you try to fit the data with the USL, the sigma value will end up being negative, and that's your superlinear detector actually. These superlinear efficiencies are not free. What do I mean by that? Well, it's like perpetual motion. It's kind of an illusion. And you recognize what is the cause of the so-called credit or constraint and figure out how to remove it. In this particular case, I've shown you an example of going from 1 disk to 4 disks per node. That's one way of looking at it if you understood that that was a constraint. By the way, that wasn't obvious to us in the beginning. Or you may have other constraints such as budgets, and this is maybe the machine you have to use, in which case it may exhibit superlinearity, but sure enough, as you scale the thing up eventually, it will cross back over that linear bound and become severely sublinear. Debugging all of this is extremely tricky, and you could never do this in a production environment. So I summarized all this in something called the Payback Theorem, which I came up with in 2012, but I didn't have data to really support it. And this came with my colleague now, Chris Thomaset, who's at Comcast, and he's now validated this theorem, as I've shown you in the data, using Amazon EC2. And that's what we're going to write up in the ACMQ article. So the takeaway visual is it's not even actually this, which is the plot I showed you in the beginning. It's really this. So even if you have superlinearity, you're going to pay for it later on in a very severe fashion. So what looks good originally turns out to be too good to be true. So you've been warned now. If you want to understand more about how to use the USL, I have a couple of books on this subject. There's a web page which has more details, and also I give training classes on how to use this. I did a Sunday tutorial explaining some of this as well. That's my presentation, so thank you for attending. And
Hi, Tom Lumicelli, Stack Exchange. Thank you for the great, very enlightening presentation. I was wondering, do you think if you look at your last slides, yeah, on the right, the areas there, do you think there might be some conservation of payback?
conservation of payback, did you say?
Like, yes.
I don't know if
it looks infinite, but I wonder if the area of the superlinear.
Yeah, no, this is just like how should I put this? This is just a schematic. I mean, don't take the upper bound region with the pink area. That just denotes the region.
Right.
And I've just done it in an arbitrary fashion. I think I know what you're asking. I don't know if there's really an answer to that question in that way. I'm kind of aware of it, but I haven't had time to think of it through in that way. So I don't think it's quite up to the standards of the conservation of energy principle, but
sure.
But I would say that it is captured in some sense by the USL. So where you get away with more than 100% efficiency, or appear to, in one region, the coefficients are fixed, and because of that, will actually cause you to cross back over the linear bound. And by the way, I didn't have time to show you this today, but if you go and look at one of the links that I provided in here when you get hold of the slides, in particular this one here, this Sunfire is now on an Oracle blog, and it shows superlinear data up through 16 nodes on a Sunfire cluster, and the fit that they do is a linear fit, which gives you the idea that this is not going to be like 150% of linear, but infinitely so. And that's completely wrong, because that violates not the conservation of energy, but it certainly violates what the USL says. So that's kind of my standard.
Hi.
Hi.
In your experiments with the Hadoop TeraSort, did you try scaling the input size up with the number of nodes you were throwing at it?
Let me think, how does that work? No, because it's a fixed amount, and the idea is that it should take less time. So I didn't show you the plot for this because I just don't have the time today. I've been showing you throughput curves, because that's how the superlinear speedup is normally represented. But we could alternately look at the run times on the y-axis. And there, as you add more nodes, you divide down the runtime for a single node by however many nodes you have, so you get a curve that goes like this. And the superlinear part actually goes faster than that. So that's essentially how it should work. So no, you don't scale up. I know you're talking about like Gustafson's law or something, but we're not actually interested in that. We're not doing any benchmarking. We're trying to produce the superlinear effect.
Right. I guess my hypothesis is that if you scaled the input size with the size of the cluster, you might get rid of that phantom superlinearity. But that's wild speculation.
Possibly, yes, because essentially you would have something like, so we use a single node to do the normalization, but then when you add another cluster and add another 100 gig or another terabyte or whatever, then it's like you've got almost two independent systems, so that should be just twice whatever you had for one. And so I think the answer might be yes, but that's not what we're trying to do. But in terms of an operational exercise, that means that you're probably very unlikely to see the superlinear effect in that case.
An alternate theory of the superlinearity is, well, you're throwing a lot more RAM at the problem as you increase the number of nodes, so they get to do a lot more in memory. And as the ratio of RAM to input data, goes down, that could be a factor in the superlinearity.
Yes, it turns out there's a whole other discussion. That is actually one of the most common explanations of the superlinear effect, and I think it may be true particularly for HPC type of workloads, but as I tried to indicate to you, actually that's not what's going on here, at least not directly. The primary effect is an I/O bottleneck, not an expanded memory. But these are coupled systems, so for the moment I want to emphasize the I/O bottleneck because clearly I can remove it. I showed you the data. If I add like another 3 spindles, boom, the superlinear thing just collapses. Independent, we didn't change anything with regard to the memory. So the memory, the caching effects, the memory effects is a common explanation, but I don't think that's, there are other things that can be going on too, so.
Thank you.
Yeah, thank you, good questions.
I'm the last one. I'm extending the time. Sorry, people. So thank you very much for that.
Welcome.
I give a talk. It's somewhat related to this in 2008 at LISA. Seeing as...
On superlinearity?
Not on superlinearity per se, but dynamic dependencies in between resources and performance improvement. So going from this, you know, the model provides a nice sort of naive physics approach at the beginning to get a sense of whether you're off your rocker on thinking that something's going to scale linearly or not right away. But seeing as P is essentially an abstract entity that represents one unit of all of the resources available to a particular, let's say in this case, a node, right? You should be able to break the USL down into subcomponents and systems and apply it to subsystems, right? Like you do in queuing theory. So disks, memory, to find out where I'm going to get the best improvement in my curve as I add particular resources for the same amount of input.
Yeah, gotcha.
Right? So what I'm wondering is if you've looked at any of that in terms of you know, putting in costs. So you basically say, okay, I've got this nice formula, and now I can potentially break it down and find out what are the contributing factors to the worst parts of my performance, and what does it cost to improve those. So I was just wondering if you've ever looked at any of that sort of from a practical standpoint of, you know.
Well, yes and no. So we'll have to have an offline discussion about it, but without getting too detailed. So my canonical position is this. With regard, so the USL basically looks at the entire system, whatever you define the system to be. In our case, it's the EC2 cluster nodes in the cloud running Hadoop, you know, blah, blah, blah.
The network bandwidth between them,
therefore the P in the formula is the number of nodes, because that's the thing that's changing on the x-axis, and that's the thing that's providing the load on the system, and the y-axis is the speed up. That's the response of the system as defined. So first point I want to make is that for example, we could think about, well, now what's going on in the network, what's happening in memory, what's happening in I/O, and of course you collect a whole bunch of statistics and so on and so forth, and how does that relate to the USL? The answer is the USL is completely agnostic about what is the architecture or how is the actual system comprised. However, it does capture the information. And do you know where that information is? It's in the two coefficients. It can't be P, because once I fix my configuration, let's say to 100 nodes, for example, then P is equal 100, end of story. Now I fit to the data over all of the nodes up through 100, let's say, and then the only thing that can be determined is the value of sigma and lambda, and those sigma and kappa, those two coefficients reflect all of the details that you're talking about in those numbers. So the second point, having made that statement now, the second point I want to make is that in doing that, it's kind of as though all of the details of whether it's the cloud or whether it's a Sunfire cluster is all compressed into those two coefficient values, because the two coefficient values will be different on whether it's the Sunfire or whether it's EC2 from Amazon. And now, to answer your question, I can't unwind those numbers. There's no way I can decompress. They're encrypted, and there's no way I can decrypt them. However, it's not a lost cause, because I've define what they mean physically, at least as far as the system is concerned. So what I have found useful, to try and answer your question, what I have found useful, and this is kind of the interesting thing about performance analysis, is I can go to engineers and say, you know, the sigma value sucks or the kappa value sucks, and these are the actual values that we've gotten from our analysis of measurements and regression analysis. Let's say, for example, the kappa value is bigger than the sigma value, so we're being hit very badly by contention, that's why we're rolling off. And then I leave it to them to think about what that might mean. So if somebody came back to me and said, well, I think it might be to do with message queuing, I would say, I think not, because message queuing would be more like the sigma value, and I'm more concerned about the kappa value, which is coherency. Coherency is not to do with queuing. Coherency is to do with data exchange between resources, such as caches, for example. It's a point-to-point exchange of data in order to become consistent. That costs time, that affects the throughput. And sort of guide people that way. Now what happens, there's kind of a miracle that happens in between where the engineers who know the system in detail that I haven't got a clue about and frankly I'm not interested in having a clue about, we work together, we play off each other, and they say, you know, I've got the idea, let's try and fix this thing. And they say to me, that will fix it. And I'll say, hang on a minute, I'll be the judge of that. You go and do your thing, and then we'll take the system back, we'll test it again, we'll measure the new scalability, I'll get the new value of kappa, and I'll tell you how good it is. And of course, life is never so simple, so of course they muck around with, and now the sigma and kappa values both change. Did you get the idea?
Yeah.
So although the details are completely and forever encrypted in the two numbers, because the two coefficients have a definite physical meaning, it's very helpful as a guideline for what engineers might think about doing in order to improve the performance of the system. Now, last point that you brought up was, you know, could I do the same thing for the various subsystems applying the USL to those within the various subsystems of the whole system? Yes, that's certainly true. Could you integrate those results with the overall USL? I don't know how to do that. That's a bit iffy. I don't know. I'm not sure exactly what that means. I'm not saying it couldn't do it, but offhand it doesn't mean much to me.
It just seems that it would be a coherent method of figuring out what to improve first, right? You can't just take it's not easy to just take the kappa value when you're talking about, let's say your node is a data center. You know, it's got, you know, to say, all right, here's how we're going to make, kappa better. We're going to increase the pipe to the data center.
I see. Yeah. So, okay. Well, in the sense, I think I misunderstood exactly what you're saying. So, in the terms of, can I go down and start to explore a particular subsystem that I think is the candidate that's offending the performance of the system? Absolutely. And just to use your example of a data center, then clearly, if I was looking at worldwide, you know, data hubs or something, and it looked like it was a data center was the issue, then I can't really tell what that might be if it's causing a bad kappa value, for example, a bad coherency term. And I would have to go in and start to find, well, engineers would have to go in and start to find out what that, absolutely, that's the natural thing to do. And then focus in on that and rinse and repeat. Same methodology, just more localized. So in that sense, yes, I thought you were talking about having a whole mathematical structure that would, okay, I misunderstood the question. In terms of empirically, that's kind of like rinse and repeat. And a focus, rinse and repeat, and absolutely, you can do that, no question.
Next speaker again, please.
No.